In this video, we're going to use Green's theorem to evaluate a line integral. That line integral is given by the integral over some curve C of 2xy dx minus y squared dy. And the curve is some sort of triangular loop. It always has to be a closed curve if you're going to use Green's theorem, and it's going to go from the point 0, 0 to the point 2, 0. Then we're going to go up to 2, 1, and then come back to the origin at 0, 0. So we want to find the value of this line integral around this triangular loop. Before we do any calculations and before we even apply Green's theorem to do this calculation for us, it's worth spending some time just thinking about what the notation even means here. This is an awkward looking expression. It's some sort of line integral, but I have a function of xy and then this differential dx, and another function only has y in it in this case, but then there's this differential dy, and it just looks somewhat awkward with a dx and a dy in the integral together like that. What are we really integrating with respect to? And the answer is it's hidden from view here. This is a line integral written in some sort of differential form. There's a parameter in there that's being hidden. So let's spend a second just thinking about what is going on here. In my picture, not only did I draw a curve, but I had the computer plot some sort of vector field. It's kind of zooming in, sweeping along these streamlines that you're seeing plotted by the computer. There's no vector field given in the problem explicitly, but what am I plotting? Well, the vector field F has two components. It's a vector field in the plane, so it has an m times I plus n times j, and in this example, m I'm taking to be 2xy as the I component, and then n I'm taking minus y squared to be the j component. So I'm reading those off from the integral that I'm given. So I've plotted this vector field, and a very important question that we can ask about a vector field is to find the work done by the field along our path C that I've drawn this triangular loop. So the work done by F around C, sometimes this is called the circulation of F around C. I'll just call it work here in this discussion. And by definition, that means to do a line integral. It means to integrate over C the tangential component of the field. So we take F dot T, where T is my unit tangent vector along my curve, and I find that tangential component, and I do a line integral around there to sum up that work around the loop. Now, what does that look like in practice? Well, what we would do is we would parameterize our curve C. So C here might be parameterized by some vector valued function R of t. It has an x component and a y component, x of t and y of t for each t, and t would go from some range of values, say from a to b. Now in practice, it's probably a lot more complicated than what I've written here because I have three pieces, and I'd probably need to parameterize each piece individually and then do some line integral over each piece and sum up the result. But in principle, we could write down some formula for the x and y components of positions around this curve and then parameterize the curve accordingly. Then you would change the variable, and you would do that by taking f dot the derivative of r, the velocity vector, and in this case you would take m and multiply it by the derivative of x. So you'd see m times dx dt, and similarly you'd take n and you'd multiply it by the derivative of y, so you'd have n times dy dt, and add that together to get their dot product. And change of variables for a line integral in this situation, for a work integral, tells you that you would integrate this dot product, which we've calculated here in terms of components, and you would integrate that with respect to time, your parameter t, over some range of values from a to b. Now, very often, this integral, which is written expressly in terms of this parameter t, so dt here, is written in a simplified form where we suppress the dt, and we just kind of think about it as symbolically canceling out with the dt's that we see here, and we get an integral that we just write in a more symbolic form, in differential form, m dx plus n dy. And in fact, that's exactly the integral that we're trying to calculate. So the problem that's given to us, this work integral here, really is a work integral for this vector field here, and this curve here. We're finding the work done by that field around C, and this is just shorthand or some sort of differential form of writing that work integral. Now, Green's theorem gives us an alternative to actually doing this calculation in this parametric form, actually parametrizing around the curve, which is going to be a lot of work. Do 3 line integrals and add them up, just a lot of work to do. So Green's theorem gives us an alternative here. Green's theorem says if you want to do this work integral, what you could do instead is do the double integral of the curl of your field over the interior of the region enclosed by the curve. And I'm going to call that region R, and that's the region now trapped in between our boundary curve here, C. And we calculate the curl of our field over that region. In terms of the components, as we've discussed, the work integral is m dx plus n dy integrated over C. And again, that's just shorthand for the line integral that you would do as some sort of integral over the parameter t after you parameterize your curve. On the other hand, the curl integral, we've defined curl to be the partial derivative of n with respect to x minus the partial derivative of m with respect to y. And we do this double integral over the region now. So in this case, the work integral is the integral that we were asked to compute. And then instead, using Green's theorem, we apply that, and we're going to take the partial derivative of n with respect to x. So I look at minus y squared, that's n, and its derivative with respect to x, because it has no x's in it, is 0. I then look at the derivative of m, here's m, 2xy, with respect to y, and that will be 2 times x, and I subtract that, so minus 2x. 0 minus 2x is the curl of my field, and we're going to integrate that expression over that region R. This is now a double integral, which in practice we'll do by doing some sort of iterated integral, by doing 2 integrals within each other to get that, that value. And so let's set that up now. It is going to be some iterated integral. I've left the limits of integration blank for a moment. We'll be integrating minus 2x. And I've somewhat arbitrarily chosen the order of integration here to be dy on the inside and then dx on the outside. And now I need to set those limits of integration. X is going to be the last integral, and my values for x range from x equal to 0 to x equal to 2. So I'm going to use those as my limits of integration for x. And then for a somewhat generic value of x somewhere in between, I need to start here at x equal to, or y equal to 0 rather. I'm at y equal to 0, and then I'm going to move up through the region until I get to this line here, and the slope of this line is 1/2. So I'm going to use the equation that y is equal to 1/2 x. I'm going to enter where y is equal to 0, and I'm going to exit where y is equal to half my x coordinate. So those will be my limits of integration for the y coordinate. I now need to integrate both of these, or do 2 integrals here and evaluate each time, and I'll do that, just let you follow through the details. When I integrate with respect to y, I'll get a factor of y, and it will need to be evaluated. Y will need to be evaluated at these limits. After doing that, I'll have minus x squared when I evaluate, and I'll need to integrate that with respect to x. And then I evaluate that between 0 and 2, and I'll get minus 8/3. And so the work done by this field around this loop or this triangular curve is minus 8/3.